let's look at general relativity. What kind of nonsense do we have over there? Well, it's just as bad, okay? So here's the list, more or less. Again, these are impromptu lists off the top of my head. I'm sure there's a lot more for both categories, general relativity as well as quantum. Big Bang creationism. Everybody believes that the universe had a beginning. You know, they talk about infinity sometimes. They talk about, you know, God existing forever, but they cannot imagine that. They talk about it, but they really can't. They really don't put anything behind it. Why would God be eternal? Who created God? Why would the world, the universe, be eternal? Someone had to create matter. And the question is, how do you create matter? How do you create something from nothing? Okay? And this is more or less what you see out there. Okay? This is the glass with beer that fell sideways. Okay? And it starts here with the explosion called the Big Bang. Okay, so we have this great explosion, and this is what they teach people. They say there's this explosion, and all this matter is pushed outwards, and when you see it sideways, which is what you see here in the glass, right? All those lines that come down, those are time slices, and we're at the present, right at the farther right, okay? So they have this nonsense, and they say this is how the universe began, in an explosion. I mean, what are you staring at? You're staring at a hand grenade, okay? That's what it is, an explosion. And then many people tell you, well, it's not really an explosion. It was that the singularity started expanding. What's a singularity? Well, it's an infinity. And so they go on and on and on. They never put an object in front of your eyes. They put a little dot, but they say, well, don't think of it as a dot. Don't think of it as a ball. You have to think of that little dot, right? The one that's going to explode there. Okay, you got to think of that as really a concept. Okay, it's what it is. You're staring at a singularity. And what is a singularity in terms of Big Bang? What means that if you take all the matter back in time, right? Yesterday, the day before, and so on backwards in time, right? So to speak. You're going to arrive at a point where all this matter was all crunched together into a little ball. But it turns out that some treat it as a little ball, and others clarify for you, the mathematicians clarify for you, it's not really a little ball. What it is all this matter is forever and ever and ever and ever coming closer and closer and closer and closer to each other, but never touching, never making that little final dot. So it's like no matter where you cut the movie, right, you're always going to end up with a little circle. And all the matter is in that circumference. Or if it's a 3D, obviously 3D, in that sphere. Okay, so it's a sphere that's becoming smaller and smaller and smaller, but never reaches zero. It never reaches a point where it all disappears or it turns into a little solid ball. It's just falling forever, approaching zero, but never reaching zero. And that's known as a singularity because it's a mathematical concept. So the universe started with a mathematical concept known as a singularity. Now you know, okay? That's what it is. Then we have space-time, the canvas. They have this space-time thingy, which is not a thingy. And a fellow called it in reverse. I like that. I think it's better to call it time-space. Because if you call it time-space, it hits you in the ear a little more, and then it maybe wakes you up, out of your hypnotism, right? Time-space is better. But what is it? What are we talking about? Are we talking about canvas? Are we talking about a fishnet? No, we're talking about something else. We're talking about number lines. That's what they are, okay? And so here, this fellow, Brian Greene, he talks about this. He says, we're talking about time as being one of the dimensions. When it's not, it's a number line. And they have these number lines which they warp. They bend them and do all kinds of things with them. But it starts with time. That's where all this stuff started. And here, let Brian Greene tell you a little bit about time. Okay, here we have this time thingy, okay? And what he's going to say, he's going to cut it into slices. He's going to, you saw this space-time glass that was turned over, fall on its side horizontal. and he's going to cut it into slices, but he's going to say something that is shocking. He's going to say that your now is not my now. You have a different now than my now, okay? Because there's a time delay between the time you see me and I see you. So if I'm traveling at a given speed and you're traveling in the other direction at a different speed, well, you're going to measure my time differently than I measure your time. And because we measure our times differently, we don't know what now is. There is no such thing as now, according to Brian Greene. So let's hear it from the horse's mouth. Here he is, okay? Give me a second here. I don't have the, I have not put the words underneath on this one. I didn't have time, but take a look at what he says. Just listen to him. Okay, here goes.
Think of space-time as a loaf of bread. Einstein realized that just as there are different ways to cut a loaf of bread into individual slices, there are different ways to cut space-time into individual now slices. That is, because motion affects the passage of time, someone who's moving will have a different conception of what's happening right now. And so they'll cut the loaf into different now slices. Their slices will be at a different angle.
Okay, so what he's saying is your now is in my future now, because there's something with light there, which has to do with measurement or something, which we don't care about. And this violates the universal movie. So let's go with the universal movie so people know what this tool is about. It destroys his argument completely and all the arguments from general relativity. Here it is. This is the universal movie. What you see in a single frame of the universal movie. This is a 3D movie, by the way. I put it in 2D. I can't put it in 3D for you. Very illustratively with an image or whatever. So what you see in a single frame there is every atom in the universe. You can say that there's gazillions of atoms. Yeah, fine. We don't care how many atoms there are. We're not going to count them. We're saying that in a single frame, God took a 3D picture of all the matter in the universe. He put it in a single frame, okay? And the next frame, all those atoms moved to a new location. Every single atom in the universe moves to a new location. So what we see in a single frame is just every atom in the universe. And so the first problem is that you cannot have different nows, because that single frame that you see there, the one that's highlighted in the center, that contains every atom in the universe. And so there can't be a future frame at the same time as that one, okay, which is what he's saying, that if that's now, what is your now? You're saying your now is the one next to it. It can't be, because if that's true, then that means you're creating new matter at every single location, in every single frame. The previous objects did not disappear. And it's not that an atom moved to a new location. It's that the new location has the same atom duplicated, has a clone of it, and so on from frame to frame. So every frame, you have new atoms. That's what they're saying, because that's the only way that your now can be different than mine and be in the future of my now. Okay, that means you're in the future of me, right? And your atoms are all there in the second frame, while I'm still in the first frame, and all the atoms exist in both frames. That means you created new atoms as we went along. There is no such thing as motion. What motion is in general relativity, according to this time nonsense that they have there, is that you're creating new atoms. Duplication. You're duplicating every atom. You're creating clones for every frame in a universal movie, which is total nonsense. That's what they're saying. Okay, so yeah, you can't use the notion that relativity has with time. There is no such thing as future, and there's no such thing as past. Father Universe only exists in the present. Every atom in the universe. That's Father Universe, space serving as background. And then every atom moves to a new location with respect to every atom in the universe. Therefore, I cannot go back in time to kill your grandfather or to meet Napoleon or Caesar, because if I can and Caesar is still there, those atoms did not change location. Those atoms stay there, and those same atoms are here today. That means that Caesar He died. All the atoms are there, right? And you see the frames of his whole entire life. All these atoms were there, right? In every frame of the film that I want to cut, there's his atoms, right? 3D atoms, right? And I go back in time and I land there, and the atom is still there because it was never destroyed. It never moved to a new location. What was done is the next frame of the Universal movie, a new atom of that atom was created. That's what they're saying. Total nonsense, total irrationality. And then you have, again, the space-time canvas there, right? Here it is. This is so dangerous, because this is what you see. This is the flat space-time. Looks like a board, but really it ain't. What you're staring at is number lines, okay? Because here, let's illustrate it correctly. This is with no object in the universe, right? This is nothing weighing it down, okay? And what you're staring at is that. You're looking at numbers, okay? So it's very misleading to say that space-time is a canvas. They illustrate it as a canvas, but what you're staring at are number lines, okay? Let's not confuse number lines with space-time, with a canvas, okay? Space-time is not a canvas. They illustrate it as such, but it ain't, okay? So just make sure you're aware of that. Okay, so what do we do that with this? Well, let's illustrate this a little better so you can really sink your teeth into it. Here it is. Okay, so you have all these numbers, right? And what you're looking at is number lines called time, and they call one space. And that's a big monster there. There's no such thing as space number line, okay, or space dimension. Okay, what they've done is they've taken three dimensions, length, width, and height, and they illustrate all three of them with a single number line, because those are number lines, and they call it space. Okay, so language here is very, very important. Okay, so what they're doing is they're putting some number lines, putting these names, time and space, and people think they're looking at a canvas, a fishnet there, and it ain't. You're not staring at a fishnet. What you're looking at is a mathematical concept which they have illustrated. Much like I showed the other day with the transverse wave. What you're seeing is not a wave. What you're seeing is a bunch of vectors that form a field, a couple fields, and those two fields supposedly are the transverse wave. And this is more or less the same thing. You're looking at a mathematical concept. Let's get that right, okay? And so what happens when you put a ball in there, on top of that number lines, right? We're going to weigh it down. We're going to bend the number lines here, fellas. Here it goes. See, that's what it looks like. They bend it. They bend the number lines. And this is totally ridiculous. I mean, this has no sense whatsoever. And, some of these people say, well, you shouldn't take it so literally. Well, I have to take it literally because this is how they're going to explain gravity. They're going to say, hey, we bend the number lines, and that's why the Earth doesn't fly out of the solar system. And here it is. Here's the illustration of that. Here, you'll see it. Okay, there you have it. This is what they illustrate. And so it's not like I'm putting words in their mouth and they're saying I'm taking it too literally. I have to take it literally because the moon doesn't fly away because there's a curved wall of warp time, warp space. There's a curved wall of space-time, time-space, that's preventing the moon from flying out. That means the moon is pushing up against a curved surface. It's touching it, or because the moon is either rolling or sliding along that curvature, and that's why it doesn't fly out of the solar system. And the same with the Earth around the sun. So it's not like, the analogy. I want them to explain the analogy. If I'm not supposed to take it literally, for real, then what was the explanation? Why doesn't the moon fly out of the solar system? I need to understand the mechanism. And if the mechanism is that, the moon slides or rolls all around space-time, well, I understand the analogy. But then they say, don't pay attention to the analogy. Okay, then what have I learned? What's the mechanism that general relativity proposes for gravity? And they do tell you that. They do tell you that mass weighs space-time downwards, and because it's distorted, it tells the mass how to move. So that is their explanation. That's the explanation of their equation, their field equation. And then they say, oh, but don't pay attention to any of that. Okay, I learned a lot today, Great. Okay, here we have the twin paradox, okay? How to kill your grandpa, is that rational? That you can go back in time, kill your grandpa, and then not be born? And they say, well, because of these contradictions, they say you can't go to the past. You can only go to the future. Okay, that means you can kill your grandson, but not your grandpa. Okay, okay. Sometimes I want to kill him. Yeah. Okay, and so let good old Brian Greene explain to you how he's going to do this magic trick of going to the future. Listen carefully. Here it goes.
Is it possible to travel to the future or the past? But surprisingly, time travel might be possible. If you could travel to a black hole, the effect of gravity on time would be huge. And if someone watched you travel close to a black hole, they'd see time for you slow down dramatically. If I spend an hour or two in orbit, something like 50 years will have passed back on Earth. I will have traveled to Earth's future.
Okay, so now you know how to travel to the future. The funny part that I saw is that there was still a check-in agent in the future. That was scary. They still have check-in agents. Okay, so is this twin paradox worth anything? Well, again, this is all nonsense. You can travel at the speed of light. If you want to travel faster than light, no problem. I'll allow that as well. Travel faster than light, FTL, right? To a black hole, to the other side of the universe, I don't care. Travel wherever you want and then come back. Hopefully, the number of times the Earth went around the sun is the same for both of us. So if the Earth went around the sun 50 times, we both should have 50 more years on our clocks. Now, if you take an atomic clock, there's no guarantee. Why? Because atomic clocks are notoriously inaccurate. And they've proven this many times by taking a clock, one of these atomic clocks, farther out. They did it with gravity probe A. They did it also with the, I can't remember the name of it now, but heating. Name doesn't come to mind right now. They took it on an airplane. They compared it against the twin clock that was on the ground, and they showed that they clocked things differently. And yeah, if you take the clock further out into space, you take it to Mars, you want to take it to Jupiter, it's going to clock, atomic clock, right? It's going to tick at a different rate. And so what have we learned? Atomic clocks are notoriously inaccurate. The most accurate clock to measure gravity is, again, a sand clock. In other words, an hourglass. You take an hourglass and you put it there, and little grains fall because of gravity. So it's the best clock to measure time. But you can't use it to go to another planet and come back. For that, you need the revolutions of the Earth. That's how we ended up with a second to begin with. We took the Earth, we chopped it into the orbit of the Earth, the revolution, and he chopped it up into little pieces, and they ended up with a second. That's how we originally came up with a second. Today they have a different measure. But the point here is that, the Earth goes around the sun, and there's no friction because you can't have friction. You can't rub your shoulder against space because space is nothing, meaning that which has no shape, right? So there's nothing there. And so the Earth goes around the sun without losing, a second. And that's the best clock there is. And so you have so many revolutions. You have 20 revolutions. Whether your twin brother goes out at the speed of light or even faster or slower, it doesn't really matter. When he comes back, hopefully we both counted 20 times, for the Earth around the sun. And that's 20 years. And there's your clock. We should both be 20 years older. No change there whatsoever. Okay, and again, time slower, closer to the ground. Well, I proved the opposite. Proved that towards the ground, an hourglass goes faster. But this is what Brian Greene tells us about the hourglass. Okay, listen carefully. Here goes.
Compared to someone living on the top floor of a skyscraper, someone living on the bottom experiences time elapsing a little slower because gravity is just a tiny bit stronger closer to the ground.
So not true, because an hourglass ticks faster the closer it is to the ground, and that is a gravitational clock. So again, this notion that they have that clocks tick faster here and slower there, well, you got to get it right. You got to use the right clock. And the gravitational clock, the best one to measure gravity, is an hourglass. Okay, so keep in mind, when you do the experiment, do it with an hourglass. Here's another fellow, and he's going to tell us about what the number of atoms increases with speed. And they have all these things, the sticks shrink by magic. In other words, they have this not only time dilation, but they have mass increase and length contraction. And they say when you travel at the speed of light, or close to the speed of light, your mass increases. Well, how can that be? Mass is the quantity of matter. So why does the quantity of matter in your body or in whatever object you have, why would it increase? Why would you have more atoms? Because you travel at the speed of light, or close to the speed of light. Why do you bloat? Because if you bloated, means that more atoms came into you, because that's what mass is. It's defined as the quantity of matter. Okay? And so we have a contradiction, because they say because you travel at or close to the speed of light, your mass increases, but they don't have a mechanism for it. It's just math. They just calculate. And so that can't be, unless they're talking about weight, meaning that you press against a scale, and so you weigh more. That's weight, not mass. But if you're going to talk about mass, you're talking about quantity of matter. Okay, and so here, let the guy from the Fermi lab tell you this. Okay, Fermi lab, that's where they do acceleration of particles which ain't particles. And he's somewhat popular. His name is Don Lincoln. Here he goes. Okay, listen carefully to him.
Without a doubt, Albert Einstein's theory of special relativity makes some very mind-blowing predictions. Clocks run at different rates, objects shrink, and things can't go faster than light. And all of these things are absolutely true. Relativity has been thoroughly tested, and there is no credible criticism of the theory.
So the good thing is that they've proven it. It's proof, evidence. You can't challenge it anymore. They've proven it. And so, yeah, all I can say is, how did the mass increase unless you added more atoms, meaning more matter? And where's the mechanism? Well, they say mathematically we proved it, and it sounds like they're talking about weight, how much something presses against a scale. Of course, if you push with your hand against the scale, your bathroom scale, it's not the same thing as throwing an elephant, or just put the elephant just standing there, right? It's going to have a certain weight. Now drop the elephant on top of the scale. That's got to go, it's got to go very much higher, because now you're talking about weight. The elephant did not increase in weight, in mass. The elephant just increased in speed, and that's pressure on the scale. And that's called weight. It's not called mass. The elephant did not gain matter when it fell. So it's very simple to overthrow the nonsense they have. And the issue is, again, they have all these different definitions of mass, and one of them is a synonym of weight, and that's the one they throw in there, and they say, well, it's relativistic mass. No, relativistic mass is just weight. It means the thing is traveling faster. It's got nothing to do with quantity of matter. That's where the problem is. Okay, and then they have all these other, same with a shrinking stick, by the way. Why would it shrink? What's the mechanism? Don't tell me my stick shrunk, and it didn't shrink in my proper frame of reference where I'm at. It shrunk from the other guy's point of view. Okay, so it's a optical illusion. The stick did not shrink. Okay, I measured my stick to be 1 meter, and I always measure it to be 1 meter. If the other guy measures it to be a little longer, a little shorter, that's his problem. He's got maybe a problem with astigmatism, or who knows. It's got nothing to do with physics, with the reality of what's out there. Okay. Okay. They have these dark spirits. They have black holes, dark matter, dark energy. Let's see what that's all about. Here we have a star, and it collapses. Okay. What does it collapse to? They say to a point. What's that point? It's a black hole. Okay. So a star collapses and disappears from sight, essentially. But they say there's something there. The elephant's gone, but the weight or the mass, right, that the elephant had is still there. And so it causes havoc to anything in the vicinity. Even in vicinity could be gazillions of light years away. You know, they have to show how that black hole, as they call it, can affect something very far away. But even if we concede that, even if we were to concede that, how does it do it? What is the physical mechanism? How does that little thing there affect a star that is, 1 light year away, for example? And they can't. And so this is the black hole. This is what it looks like. This is what a black hole really is. Okay, these are the pieces of a black hole. And you can see what it has. It's got a singularity at the center. What's a singularity? Well, again, take your pick. It could be a little ball, right? Right at the center. That ball has 0 dimensions, 0 volume, 0 everything. There's nothing there. It's got no shape. Okay? That's one notion that people have out there. All matter is crushed out of existence. There is no matter within that radius, the circumference there, right? And that's one notion. The other one is the singularity is really something else. It's runaway math. It's infinity. Matter is approaching the singularity, but never reaches. And so the question is, how do they have these spaghettification, where they say that if you survive spaghettification, you go through the little hole and end up in another universe? Well, hold it. I thought you said we never reached the singularity. But then they have you go into another universe through a wormhole, through that little tiny zero-dimensional hole, whatever that is. So it's all poppycock. It's all nonsense, garbage. None of this survives rationality. You cannot say that what they said is rational. And again, the event horizon is again like the campfire. Think of black hole as a campfire, the center, the singularity, right? Think of it as a campfire, and the event horizon is like the heat. Okay, how far does the heat from the campfire go? Well, let's say 2 meters or whatever, 3 meters. It doesn't matter, right? Well, that's the event horizon. It's the region of influence of that campfire in the center. That's essentially the notion of an event horizon. And so we have a singularity, which is absolutely nothing. It's a zero-dimensional ball or infinity where matter is falling and never reaching the singularity, except you who can make it through the little hole and go to another universe. And that nothingness there, that zero-dimensional whatever, singularity, right, has so much mass that it creates this event horizon, its region of influence. And anything within that region, if you pass through there, well, then you cannot escape, because no matter can escape at the velocity of light. No matter can travel at the speed of light. Okay? And so, yeah, these are the little theories that these people have. Take them or leave them. I don't know what to tell you. This is all nonsense. This is poppycock. This is what's coming out of respectable places like Cambridge and Harvard, right? So keep that in mind. This is official. This is what you're paying for, because a lot of your money, from your tax, goes to these places, and they pay the so-called mathematical physicists, right, to do all this work, to do all these calculations. Then they come back and they give you this irrational explanation. They have no idea how this universe works in quantum and in general relativity, in the micro world and in the macro world. They have no clue whatsoever. And of course, the famous wormhole. Here's the wormhole. Okay, if you've never seen one, let's look at it. Here it is. That's a wormhole. And what you're staring at, you might say, Bill, you're kidding me, is 3D, 2D. No, it's 1D. It's one-dimensional what you're staring at. It doesn't look one-dimensional. In fact, it would look like it's a three-dimensional whatever on a two-dimensional background. That's what it is. There's no one-dimensional anything in what I'm staring at. That's your wormhole. And supposedly it's what takes you to another universe. So I don't know what to tell you. These are the nonsensical things that they illustrate. And you say, well, maybe math cannot be illustrated. Well, if that's the case, like, you have some people, you have Sabine Hossenfelder and some of these other so-called mathematical physicists, right? And they tell you, well, really math should stay with math because we cannot really put in ordinary language, in ordinary speech, our math, our calculations, our notions, our concepts that we have in math. Well, then that means math is not the language of physics, because physics is physical interpretations, causes, mechanisms. I need to see something. I need to see what the mechanism is. They don't have a mechanism for anything. And so the question is math the language of physics? And the answer is a resounding no. Okay, it's not. We don't use math in physics. What we use is objects. You have to have an object. If you have an object, then you can put it in motion. You can show a mechanism, and that's physics. But to say that, you did some math and you tell me how something moved, and that something is not a something, it's a concept, which is a nothing, then we have a problem, because now you can't give me a physical interpretation, which is the physics part of mathematical physics. Okay, so that's where the problem is. They're not doing physics, but they claim to do. They call what they do physics. Okay, and then here we have, just in case, we have this, which is the funny part, because they have this dark matter, dark energy, which is 96% of what they don't know about the universe, and the matter that they are aware of is only a 0.4%. They have 3.6 non-luminous, 23% dark matter, 73 dark energy, and that tiny part, the 0.4, is what we see. What we can see, what we can measure, that kind of thing. And the funny part is when they say that that's a measure of their ignorance. In a way, I do agree, but no, they even got that wrong, because the fact that 99% of the universe is, they don't know what's out there, is not a measure of ignorance. Ignorance is, if you have 99%, ignorance is when you're a mathematical physicist. Then you have 99% ignorance. But you cannot say that because all this dark stuff out there that you don't know anything about is a measure of your knowledge. No, it doesn't follow, but this is how they put it. Anyways, you can see there that this is how they break it up. They're looking for this stuff. A lot of money is going into dark matter research and dark energy research. And they say, hey, we got job security because, 99% of the stuff we know nothing about. And so they got a lot of money there for research, right? They can research this forever. What they're researching, they're doing, inventing math. That's all they're doing. And finally we have the multiverse. Okay, just like we had the many worlds in this, in the general relativity world, they created the multiverse, meaning there's a bunch of universes, and where every step you take, you end up with a different, a different place. And again, a lot of this stuff has to do with rebirth, right? The fact that you come back from the dead. So, these are not new concepts. They've just introduced all this stuff, into physics, into science. They just took it from these religions like Buddhism, Hinduism. They say you're going to be reborn, etc., and then you come back in your next life and whatever. And that's what all this is about. It's a way of introducing religion in the guise of science. They just took these same ideas, put them in there, and we're done. And that's how they explain these things. Okay, so what's the bottom line? Well, I have a little corollary for you. Let me take this one out of here. Here's the corollary to all this. And this is it. The most astounding failure of mathematical physics, right, which testifies to its irrationality, is that in the last 5,000 years, really more, right, mathematicians have been unable to discover what causes a spoon to fall to the floor. Here I have a spoon, right? I let go of it. Very simple experiment, very simple experience that everybody has gone through in their life. Something falls from your hand, falls to the floor. Little spoon, right? Plastic spoon falls to the floor, right? And they cannot explain the simple phenomena. And then I think that shows how much mathematical physics is really worth. They cannot explain something as simple as that. And all they had to do all these years was identify the invisible objects that come in physical contact with a pen, with the spoon. Because the issue here is that this would not fall if something were not pushing or pulling on it. Something is in contact with every atom of this spoon. So, because if we have it in outer space where there's, no physical object close by, it doesn't really fall. But it just stands there, kind of, maybe floats around, who knows. But for it to fall, it's got to have something in contact with it, and you have to have the Earth, a moon, some object, some planet, some big object, right? And then something from that object must be touching the spoon for it to move downwards towards that object. And for you to say that there's nothing there or nothing here, nothing at all here because you can't see it or touch it, that's where the error is. And that's where we're at today. So for those of you who like mathematical physics, just keep listening to the authorities, and they're never going to tell you how this universe works.